George Fakes and Daniel Lamb. Uh, they are medical students and researchers at the University of Texas Medical Branch, where they work at the UTMB Medical Prototyping Lab. Today, George has focused on using 3D printing to fund a toy drive, which has raised over 1,000 toys for pediatric hospital patients and $20,000 for student scholarships in the past 4 years. Daniel Lamb has experience establishing startups and commercializing 4 medical technologies through UTMB's Department of Innovation and has used 3D printing to innovate robotic surgery training in the field of otolaryngology. Give them and their talk, Refining 3D printed Tungsten Shielding, a collaborative approach to clinical customization, a warm welcome.
Okay, good morning, everybody. It is so nice to be here. And I would like to thank you, Oshwa, for allowing us to give this presentation to you guys. We're really excited. So basically, my name is Daniel Lamb, if you guys haven't met us before yesterday. And this is my good friend, George Faquez. And we're here to talk to you a little bit about 3D printed tungsten, which is something we're really excited to share with you guys today.
Yeah, so to give a brief overview of what we'll be discussing today, first we're going to be talking about our background, just kind of who we are, how we got into this. Second, we're going to be kind of explaining a little bit about radiation therapy. Third, we're going to be discussing tungsten filament. I don't know, you don't know what that is, but don't want to spoil it too much. And fourth is kind of its inclusion in open source.
Okay, so just to give you guys a little bit of a background about who we are. So George and I are really good friends, and we actually met freshman year of undergrad. We worked on a bunch of different projects together, and we shared a lot of visions together, and so it really just clicked. And since then, we've developed a lot of different things, products, projects, clubs, and we've been working together ever since. And recently we found out, last year, we found out that we got into the same medical school, and so we continued our journey together in medical school.
Yeah, and so this is kind of how we got into 3D printing. So it all started, I guess, for me about 8-9 years ago. I was a sophomore in high school, and I was a book nerd, and I was always in the library. And the librarian was telling me how she had just bought this really cool new thing called a 3D printer. It was maybe less than a foot tall. It could maybe do something that was like 1 by 2 inches. It was really, really small. And I had asked her, I was really big into video games, could I print like a little video game character? And she was like, sure. And it was really bad quality, but it did its job, and it opened my mind to like, wow, this is a really cool technology. I didn't even know this existed, and it was so new at that time. As I got into college and went to graduation, or as I got into college and did undergrad, I was walking in the science labs. I was a bio major, and one of the labs had a lot of different huge moving orange machines. I talked to the lab director there, and I found out those were 3D printers. They were very different than what I remembered them looking like maybe 3 or 4 years ago. And we had one that was literally the size of a closet. I think it was about 4 feet by like 9 feet. It was this huge 3D printer to see how much it changed. And so that really got me into it. You see the photo on y'all's left is a 3D biomolecule microtubule. So that was the first course I took in undergrad about 3D molecules and design. It was about understanding the complex mechanisms of proteins and understanding the 3-dimensional shape and how proteins work together in the human and how their shape really affects that. And so the director was just really, the professor was really involved in 3D printing and wanted to combine that. And so from there, that was my first print I ever did. It was about a foot tall, and I designed my own microtubule, finding the dimerization of it, a whole lot of nerd stuff, but I created basically one of the building blocks of life. From there, I really just enjoyed it. I saw the opportunities that could come from 3D printing, and I wanted to maybe do some things for change. One of the things I thought about was maybe designing some 3D printed ornaments. And that was whenever Daniel saw me working on 3D printing. He was asking me what I was doing, and I showed him a little bit what I was doing, and he caught on so quick. He was a natural. And from there, we started making a yearly toy drive. You can see in the middle, this is one of the booths we had. We basically custom designed different ornaments for our university and sold them in exchange for toys. And so within our first year, I think we raised 200 toys. And then from there, we just kept expanding on and concluding and making it bigger and bigger and bigger. And from now, it's been over 4 years. We raised over 1,000 toys for pediatric patients. We raised over $1,000 for Houston women's shelters, and we raised over $20,000 in scholarships for undergrad. Thank you. And we're planning on continuing it again this year with UTMB. And so we're looking forward to continuing that. And then you see on the right, kind of going now into medical school, this is something that Daniel had worked on called DAX, the little robot for pediatric patients with the AI scribes. They don't want to see a little robot, they don't want to see just a phone recording them while the scribe is kind of writing what they're listening to in the patient encounter. So Daniel had come up with the idea of what if they are seeing a robot that they're kind of listening to. And so that's something that Daniel had worked on.
Okay, so as we transitioned into medical school, we really wanted to see how far our 3D printing hobby can kind of take us. And we kind of understood that there was some 3D printing in medicine, but once we got there, we really understood like the true breadth of the things that you could do with 3D printing. So 3D printing in medicine is very, very common, actually. It's been done and implemented at a bunch of different subspecialties around the medical field. And one of the biggest things was that I found out that you could take a CT scan and convert it into a 3D model of the patient or any of their limbs, their bones, their skull, or anything like that, and actually build off of that. So in the field of orthopedics, this is done all the time to create custom implants for patients, like bone implants and things like that. There's a lot of surgical guides that have been invented. And so really, once we got here, we were like, hey, this is something that we can really expand on. There's more to this than meets the eye. And so we really realized that we could take our hobby as far as we wanted to go. And so that's where we discovered kind of a little bit about radiation therapy. Okay, so a little bit of background here. I went and shadowed a doctor for radiation oncology. So they treat patients that get cancer with beam therapy, different types of radiation therapy. And so it was really fascinating to see. Basically, radiation therapy is if a patient comes in with a cancer, whether it's a brain tumor or an intra-abdominal tumor or like a cervical cancer, they can be a candidate for radiation therapy where you basically have this linear accelerator inside the hospital room and the patient will sit and they'll get basically a concentrated blast of electron beams into where the tumor is. So the physician will sit there and kind of basically draw out and map out where that tumor is and then give it to a physicist. And then the physicist will use that and basically give the instructions to the machine to kind of cure cancer in patients using radiation. It's really cool stuff. So to give you guys a little bit of an image, the linear accelerator basically rotates around the patient 360, and then using different shapes, using kind of different materials to adjust the shape of the beam, we can kind of concentrate exactly where we want the beam to be to treat the patient intra-abdominally without having to do surgery for them.
Yeah, and so one of the additions to electron beam therapy that Dana was discussing is something called brachytherapy. It's a form of internal radiation that actually will deliver the targeted radiation seeds directly into the patient. So it's not like they're just shooting beams, they're actually taking small seeds. And it kind of says right here some of the things they use: iodine, palladium, iridium, some scary names, and they're basically directly injecting it into the patient. And some of the use cases for this is things like prostate cancer, breast cancer, cervical cancer, where it's usually deeper in the body cavities, and they don't want to just do kind of broader radiation or electron radiation. And so the goal of this is to really target just that area without really pushing all the other areas around it to getting more damage. And I know what you're thinking: what is that collateral damage? So a lot of things in medicine are really comparing the benefits versus the risks. And so we can see here for brachytherapy specifically in conjunction with electron beam therapy alone in these specific cancers, it's really beneficial. So currently brachytherapy is used in almost every single case of cervical cancer. The reason why is they see it changes lives. So you can see the numbers on the graph. So when brachytherapy is included, the 3-year disease-free state is 79%. That's a 12% increase. When we're looking at the big numbers, hundreds of thousands of people in the US get electron beam therapy every year, millions in the US, or millions in the world, sorry. And so this 12% increase in saving lives is a big number. And so it's really important that whenever we're doing these things, we're really considering those risks, considering what does it mean to inject someone directly. And like I said, the benefits in this case definitely outweigh the risks, but it's definitely something that's constantly on the physician team's mind.
So in the field of radiation oncology, collateral damage is something that the physicians think about constantly. We are constantly, like George was mentioning, kind of weighing the risks and benefits of the procedure. We don't want to give radiation to patients that don't need it, right? But so there's a whole slew of research in the field of radiation oncology that is working on trying to prevent and block collateral damage for patients. So there have been systems implemented to prevent motion in patients, kind of comfortably keep them in place so that we don't get shifting of the radiation therapy, or there are different ways we can kind of make the process more consistent for the patient. So, organs inside your body will shift around, right? They're not consistent. So you can create boluses to kind of hold those cavities in place so we can treat the tumor more consistently. And so a lot of the big talk about radiation oncology is how can we prevent additional radiation from reaching parts of the patient that don't need to be reached, right? So we can treat it effectively. We can be more kind of liberal with our treatment as long as we have enough leeway to protect the patients from additional radiation exposure.
Yeah, and when anything involving radiation is involved, usually, I know y'all have recognized this, whenever y'all go to the dentist's office, they put it when you're getting x-rays. It's really important for usually the entire team to be wearing stuff like this. It's basically a shield that you put on top of yourself. It's usually made out of lead, and it basically does exactly that. I know it doesn't really make you feel comfortable whenever the doctor's like, oh, everything's fine, and they start the machine and they run out of the room as quick as they can. And so it doesn't really make that reassuring. But once again, there are things like this that help everyone. And so this is usually, like I said, made of lead. It's usually only placed on top of you. And the reason why they use lead is it's extremely radio absorbent. It helps absorb a lot of that radiation to protect those other organs that we want. And the thing is, that is not specifically a trait with just lead. There are other properties of metals that have that same property. One of those being bronze. Bronze is also pretty radio absorbent. Another one is tungsten. Tungsten is extremely radio absorbent. And the thing that's different than lead is it's not really toxic. Everyone hears about lead poisoning, lead toxicity. So why don't we do something more like that? And the thing is, there's a lot of problems with tungsten. I think y'all probably know this figure a little bit more than I do, preaching to the choir, but CNC machining is one of the big ways that we actually use tungsten to basically get it to the product we want. One, we know how expensive that process is. Two, how hard it is to actually bring this into a direct patient care. There's not really much ways to kind of tie those two together. One, like I said, the process is pretty hard. Usually it's pretty wasteful too. You have this big sheet of tungsten, and basically in these huge CNC machining, you're basically having to sculpt out the product you want. So you're losing a lot of that actual raw material, first of all. And two, the customization, one, really isn't there. It's huge machining. Like I said, processing cost isn't there. But if only there was kind of a way that, how can we manufacture this a little bit better?
So this is where we kind of want to talk about the new kid on the block. This is some really exciting stuff that was developed a few years ago. And it's a tungsten polymer hybrid. So there's this company called Prusa, you guys have probably heard of them, that developed this polymer that has tungsten powder embedded into PETG. So it's 75% tungsten by weight, and it shares a lot of properties that tungsten has, but also has the manufacturing ease of 3D printing, like a normal thermoplastic. And originally this product was developed for nuclear pharmacy, where it's really, they need to develop like pharmacies that compound chemicals for chemotherapy. It's actually really dangerous to manufacture and ship those products to hospitals worldwide. So one of the things that Prusa came up with was, hey, let's find a way to easily create custom packaging for nuclear pharmacists to be able to make their medicine and ship it easier to hospitals. So we wanted to take that idea and kind of convert it into the field of radiation oncology, where, hey, custom face shields, custom implants for patients to protect them from radiation therapy. This is a really, really good use case for something like this. So let's look at the actual attenuation of performance of something like this. So it's, some made of plastic. So how much better is it? How good is it at blocking radiation? So actually, the red graph here is the radiation attenuation performance of this tungsten filament by thickness. So once you approach 1 centimeter of thickness, it becomes just as radiation opaque as tungsten and lead. So this means that you can create very clinically viable shields that are only 1 centimeter thick, that has just the same level of performance as something like a full sheet or block of tungsten or lead.
So cost of production, we know, especially in something like healthcare, cost of production is a very big factor, especially if we want implementation into things like hospitals, things like that. They definitely want to be looking at these numbers. And so is it actually cheaper to be doing this? And so one, we're looking at the left graph, we see the material cost. The material cost of tungsten is around $240 per kilogram, while the material cost of the polymer, the filament, the tungsten filament, is around 230. The thing is though, two things. One, sometimes those costs can kind of vary. So we're going to kind of give that an equal thing. But the thing about the tungsten CNC machining is, like I mentioned before, it's extremely wasteful. You have to start with this huge block and bring it down and kind of sculpt it. So sometimes you're not even using 100% of that block. You're maybe only using 40, 50% of that block to get that desired product you want. Compared to 3D printing, most of y'all know how we kind of build it from the ground up. It's extremely wasteless when it comes to the actual material to the product. And if there is some waste, it's usually going to be in a kind of form of support material. And the good thing about 3D printers now is you can actually change what that support material is to maybe use it something like a cheaper material for the support. And so you're only using that $230 kilogram, the expensive PETG, for the actual product you want. And the most important thing in this case is going to be the production cost. So about an hour cost of CNC machining is about $100 per hour. And if you were to go to a 3D print farm, it'd be about $20 an hour. But most of us don't use 3D print farms anymore. Most of us have it at our homes or at the universities or at hospitals. And so in reality, it's usually a one-time cost. And this is maybe Gen Z math, but after that, that means it's basically free. So every single time after that, you're not really using material costs for actual processing. And so from that, all you're really using is the material cost of that $230 per kilogram, and you don't have to worry about this constant CNC machining fees. So really cool uses.
Okay, so the really cool thing is that the printing process is basically the same as every other thermoplastic printing that you would want to do. The only difference is that you would have to change the nozzle in your printer to a hardened steel nozzle. That is a fairly common upgrade that you make for most 3D printers. But other than that, that means you can use and print tungsten filament at home with proper ventilation, of course. But, you know, this is way better than you trying to machine your own like tungsten, I don't know, like shield from home.
Yeah, so safety and quality considerations. Because this is a more newer filament, there isn't too much research on it in general. But what we have to do is kind of break it up. So like Daniel was saying, it's a combination of PETG and a combination of tungsten alloy. So innately, both of those are biocompatible. They don't cause any toxicity. And the thing is, whenever they actually created this product, the combination filament, there wasn't really any chemical changes. It was just physical changes. And so we hypothesized that there shouldn't really be any innately different biocompatibility. And so there isn't a direct biocompatible label on it yet, but there isn't not one. So that's why we're just saying this is maybe something that we need to look forward to and research. And is it actually biocompatible? And based on the science, it should be. And so how can we use this in healthcare? And some of this is like kind of what Daniel mentioned, 3D printed tungsten shields. A lot of the things of radiation therapy that we talked about is collateral damage. So what if we combine that with something like tungsten? You're not using lead anymore, so it doesn't have to necessarily be on the outside of the skin. And there's a way that you can 3D print it to be customized per patient. So like in this case, you're literally just putting it on top of a patient. You can customize their face and be able to reverse engineer it and literally make a custom shield. Another thing was the whole brachytherapy I mentioned before. If we're doing something around the cervical area, there's a lot of important parts around there, and there's a lot of risks that come with directly putting radiation there. You have your genitourinary area, just kind of your rectum is right behind. You have all your reproductive organs there. And so do we really want to be blasting radiation surrounding that area? So if we can custom make a shield for those areas to make sure whenever we're putting this radiation inside a patient, it's not kind of going out and blasting all of its surrounding areas. And so how do we maybe do that?
So let's go through a little bit of the clinical workflow of how you'd be able to implement something like this for patient care. So whenever a patient comes in and they have a cancer, we kind of analyze them to see if they're a good fit for radiation therapy. And if they are, they're sent to get a CT scan. So that CT scan is already done for this radiation therapy anyways. What we can do is we can actually take that CT scan and then put it in a program called 3D Slicer. 3D Slicer is the program I mentioned to you guys before, where we can convert patient CT scans and DICOM information into 3D models that we can build off of. And so from there, we work with the physician in order to build and custom print a shield based off of the patient anatomy and based off of where that tumor is and what we want to protect. And so we use generic CAD files, CAD modeling, and use a readily available free program on 3D Slicer to be able to implement something like this for patient care. And so there's another study that has been done, not by us, but by a different institution, and they did the same workflow, but instead of using tungsten, they used bronze. So the images I showed you in the last slide were with bronze filament. So they took a CT scan of a patient and they custom fit bronze shields for the patient, and it actually showed that they achieved a 95% dose reduction and improved fit and comfort. The good thing is that this workflow, because it's 3D printed, is easily adaptable to the tungsten filament. We literally just swap the filament, the printer stays the same, the workflow stays the same, and the process stays the same. And so we can actually create a much higher efficacy of radiation attenuation with very little modifications to an already existing workflow. Oh, yeah. And so I wanted to talk a little bit more about like how this all ties into the open source thing. And I know we talked a lot about 3D printing and open source yesterday, but the nature of 3D printing is inherently open source. Whenever George and I got into 3D printing, we used Thingiverse, MakerWorld. These are all readily available websites that allow you to take and modify designs for free online. We really use this to we took it really far. But basically, what I'm trying to say here is that this means that the distribution of files and the distribution of the workflow is really easy. We can transfer this information to hospitals and implement this to a wide set of patients much quicker than if we had to develop like a CNC.
Patient. That's something that I think, take that privilege really highly, and it really is an honor in this kind of innovation team working together with engineers and collaborators of actually being the ones to speak to the patient. We are seeing them before they go into these therapies, during the therapies, and after, making sure that everything is staying good, making sure that we bear that responsibility of keeping up with that patient. And so it really is about this collaboration effect, this innovation team that works together. And I think this presentation is kind of a tribute to that. The engineers at Prusa did their jobs. They found this really, really cool, broad, useful 3D printed tungsten filament. They didn't really give a specific use for it yet. And so it's our jobs as future physicians, seeing these patterns, seeing how can we make a change and connecting those dots. So it's really that intersection that we as a team need to work together to really make an impact, figure out that concern, and find the solutions together. So thank you all very much. We appreciate all of y'all. Thank you.